So let's review what we've already learned. The first thing that we know about is nuclear decay. So we talked about nuclear decay process and how this is a natural, spontaneous emission of radiation that happens in sources that are normally around us, like rocks, that sort of thing. That's where there are certain very dilute forms of radiation, like uranium, just naturally existing in the ground. And there is natural radiation, but it's at very, very low quantities normally. The second type of nuclear reaction I want to talk about is nuclear bombardment. Now this is one that you might be a little bit more familiar with because it happens in nuclear power plants. So this is when you take a nucleus of one atom, so you'll take an atom and you'll hit it with a nuclear particle, a particle of some sort, and that particle will come in really hard and fast and it breaks the atom apart, and that produces a lot of energy. And this creates different types of atoms, and when it breaks the atom apart, it also emits radiation and it emits heat, which is why it's useful to us as a form of energy. And so that's what goes into our nuclear power plants. So let's take a look at what this looks like when you actually envision the atoms. So if you remember the famous Einstein's law, E equals mc squared, this tells us that energy is related to the change in mass of an atom times the speed of light, that's c. So that's the speed that the particle is moving at. So we can quantify how much energy is produced by a nuclear reaction using this law. So what's happening, say, in a normal nuclear reactor is you have this enriched uranium, uranium-235. This is an isotope of uranium. And there's an incoming neutron. That's what this N stands for, is your neutron. And it hits the atom really hard and fast. And what happens is now that the atom is unstable, because it's heavier now it's 236, it can't quite hold its formation, and it breaks apart into two smaller atoms. It turns into krypton and barium, and when it does so, it releases a ton of energy. All this energy comes out because its mass is very heavy, right? And the speed of light is something like 3 times 10 to the 8 meters per second. So you're getting a ton of energy coming off. This is mega electron volts. That's what that is measured in. And not only does it release these atoms that are broken apart, but it also releases more neutrons. Check out these neutrons coming out. So you get these neutrons that come off the reaction too. And so what that does is these go on to break up other atoms, and they hit other U-235 atoms. And so that's where this chain reaction in a nuclear reactor comes from. Once one of those atoms breaks apart, it releases more particles, and those particles go and break other atoms and other atoms and other atoms until all the fuel is used up. Another thing to keep in mind, like I had mentioned, is that U-235 is a specific type of fuel made for nuclear reactors. So in the environment, we normally encounter U-238 most of the time, which is the stable form, the unradioactive version of uranium, whereas the U-235 is an isotope that is reactive. However, in nature, normally you encounter primarily the U-238, and only 0.711% of all uranium atoms are U-235, which is a pretty low percentage. Now, in order to make fuel for a nuclear reactor, you need somewhere about 3 to 5% U-235. So that's where that enriching comes from, is there's a much higher percentage of this isotope in the uranium that's used in nuclear reactors in order to get enough energy out for it to be useful. Now, the history of nuclear fission is very interesting. It was actually discovered in 1939, just before the Second World War, and the discovery of nuclear fission and the harnessing of it happens extremely quickly during history. So we see here that this was published in Nature, the discovery of disintegration of uranium by neutrons. And this is a new type of nuclear reaction, nuclear fission. And you can see here that they go on to describe that barium is formed of a consequence of this disintegration of uranium. And you're seeing all this energy come out of this reaction. And then that goes on to be the project that begins the enriching uranium project. So once they figure out that this needs to be done, they figure out, oh, we need to enrich uranium to run these things. And so they're starting to figure this out because of the war. So the war is ramping up here in 1942. And then in 1945, they're using nuclear weapons. They're using this as a nuclear weapon. By the time it was discovered in 1939, so within 6 years, they discovered this technology and they used it to make bombs. So very, very quickly. And then we get into our more modern history of nuclear energy, where we're using this power for energy instead of weapons primarily. And so we see nuclear power submarines, and we see our first commercial nuclear power plant in 1954. So something that I hope you learned from this is that nuclear decay is not the same thing as nuclear fission or nuclear bombardment. So you can have, with nuclear decay, natural emission of neutrons. This is, again, a neutron. But this is a decay process. The reason it's a decay process is because it's not initiated by anything. So nuclear fission has to have an incoming neutron. It's got to have a neutron come in and strikes the atom. Strikes, I can't spell, strikes atom. Okay. Okay, so there's an action happening. It doesn't just naturally hang out and then emit neutrons. That's nuclear decay. Okay, so using what I just said and the knowledge that you've learned, which of the following of these reactions is a nuclear bombardment reaction, i.e. a nuclear fission reaction, and which one is a natural nuclear decay reaction? So the way that you know this is by looking at where the neutrons are going in and coming out. So we're seeing for this one here, we have neutrons coming in, so that means this is an initiation process. Whereas for this one, we have neutrons coming out. There's no neutrons coming in here. This is nitrogen. Remember that the symbol for a neutron is this. So there's none of this on this side of the reaction. So this is the decay, and this is the fission, or the bombardment. Now, nuclear energy is super useful because it emits a ton of energy. Another of the important things about nuclear energy is that low quantities of fuel are required. So to make a ton of energy, you need very, very small amounts of fuel, like not much at all, or not much uranium in the samples that they're using. Because remember that the uranium they're digging up is only 3 to 5% U-235. So you don't need too much of it in order to get a lot of energy out of it. Another thing about nuclear energy is that it's clean-ish. So you aren't emitting things when you burn nuclear fuel. You're getting the nuclear waste off of it, which is isotopes. There's no emissions into the air. It's also very reliable because you can, it's from a chemical reaction, so you can run it whenever you need it. Another thing is that it doesn't, again, contribute to global warming because it doesn't emit CO2. What it emits are the isotopes that come off of the chemical reaction. The nuclear power plants usually have a low operating cost as well. And what's also nice about this is because radiation is normally harmful when you're super duper close to something, but when you're really far away from something or you're at a distance, there's not really going to be a health hazard for people that live near a nuclear power plant. Whereas if you live near a coal power plant, for example, there's a much more significant health risk being close to that. Now, there are cons with nuclear energy, and this is an important conversation to have right now because we're going through the energy transition during this time of our lives. And so you're going to see some debates about nuclear energy. So some of the issues with it is that once you have these chemical isotopes that come from nuclear waste, is these things have to be stored until they're safe to be around because they take a really long time to degrade, sometimes hundreds, thousands of years. And so you're seeing nuclear storage under places like Yucca Mountain in order to hold this stuff until the time at which it can safely be released into the environment. Nuclear is also not free of mining. We got to get the uranium out of the ground somehow, and so that is happening. Another thing is that transporting radioactive materials to the nuclear power plants does have a high cost because of safety measures. And there are instances of rare accidents happening. So I showed you the Fukushima disaster. These things very rarely happen, but when they do, they are very significant. So that is a safety concern. And nowadays, power plants are getting more and more safe as the technology develops, but that is a thing to consider. Another very important thing about nuclear energy is that it's a non-renewable resource. So once we use up all the uranium, it's gone. It doesn't come back. Just like oil and gas, that sort of thing, it's a finite source. And what's really interesting about that is I looked it up, and it sounds like we have about an 80-year supply of nuclear fuel left at the current consumption rates as of 2022. Which is not very long. However, back in 2009, so a little over 10 years ago, it was estimated there were 230 years of nuclear fuel left. So we have increased consumption rates dramatically over the past 10 years, going from 230 years to 80 years left in the span of only 10. Like, we didn't go through that many years, but we're seeing a dramatic reduction just as the world grows and there's more people that need more energy as the world is progressing. So most of the nuclear power plants that may come online, if they're using uranium fuel, we don't have enough of it left for them to run a significant amount of time. So there is an issue with that. Let's again reiterate the types of nuclear reactions we've learned about. We learned about nuclear decay, which is a natural process. We learned about nuclear bombardment through fission, which is where you're hitting a heavy atom with a neutron in order to split it apart and get energy. We're going to talk about one more type, fusion. Nuclear fusion is an interesting phenomenon that primarily happens on main sequence stars out in outer space. And the difference between nuclear fusion and nuclear fission is that it uses lightweight atoms. So with nuclear fission, we were talking about really heavy uranium atoms that are big and bulky, and they've got lots of protons and neutrons in them, whereas nuclear fusion, we're talking about hydrogen primarily, sometimes helium. These only have one proton in them. All right, these are very, very, very small. And they're taking those two together and smashing them together at heavy temperatures and pressures in order to form heavier elements like helium. So you can see an example of some of these reactions where we're smashing our hydrogen. Actually, this is deuterium because it's a weight of 2. It's got one proton, one neutron. And they're smashing that together to get helium, and a neutron comes off of it. This is another type of reaction that's happening. We're getting tritium, which is an even heavier hydrogen. So it's got 2 neutrons, 1 proton. That's where this mass is coming from. This is a normal hydrogen atom, so that's stable. And then we've got a smashing of deuterium and a helium atom to get another helium atom and a stable hydrogen. These are stable. And you can see that there's all this energy being emitted each time one of these things smashes together and fuses into a heavier atom. Now, one of the problems with nuclear fusion is that in order for it to occur, it's got to be really, really hot. So the sun's usually about 5 million to 100 million degrees Celsius in order for this process to happen. So this normally doesn't happen on Earth because of this issue, and also has to be pretty high pressure because you have to contain this reaction. Another thing that's really interesting about nuclear fusion is the products that it puts out are either stable, this is not radioactive waste, or the radioactive elements it does put off, these isotopes here, decay really, really fast, like a couple of years, they'll be gone, you know? And so nuclear fusion doesn't really emit radioactive waste, and what it does emit is very short-lived and goes away really quickly. So it's pretty clean on the waste side. So let's go over the differences between nuclear fission and nuclear fusion that we've learned so far. So these things are similar in that they both change atoms' nuclei. They create new atoms entirely. There's large amounts of energy that come off of both of them. You're seeing, again, a new element being formed from something. However, they are different in that fission uses large atoms. Fusion uses small atoms. You have radioactive waste from fission, that has a long half-life. This stuff has to be stored in order for it to be safe, whereas fusion, you have little to no radioactive waste. And then this normally occurs in nuclear power plants for fission, and you have nuclear bombardment happening, whereas nuclear fusion does not happen at room temperature. You need really, really high temperatures in order to get it to go. And if any of you are familiar with Back to the Future, the movie, you will understand the significance of nuclear fusion and why it's important. So let's take a look at the significance of nuclear fusion in the development of our galaxy and all the elements on the periodic table, because fusion is where these things come from.
Hydrogen and helium are forged by stars.
Stars are really interesting. They don't just sit there. They know because they last so much longer than we do. We think they're permanent.
Stars are the ultimate alchemists. They turn light elements into heavier ones. They get the energy that they need to glow that way. A star begins its life made out of hydrogen and helium mostly. About 70% hydrogen, 28% helium in the case of the sun.
In a star's core, the temperature and pressure are so high that hydrogen atoms fuse together to make helium.
This is the fusion, nuclear fusion.
Hydrogen fusion releases prodigious amounts of energy, the heat and light of a star.
That's the story for 90% of the life of a star, fusing hydrogen to make helium.
And our sun is currently doing
that. The star
that.
runs out of hydrogen and begins to fuse its stocks of helium, making yet heavier elements.
And so the way it works, and it always works this way, is that it contracts and it gets hotter. And if it can find something new to burn, whether it's the kitchen sink or coal or whatever, it'll burn it.
Helium is taken 3 at a time to make carbon.
So now it's fusing helium to
that
make carbon.
And make element number 8, oxygen.
That's a tremendous step forward. You get carbon and nitrogen and oxygen made in stars.
Now this is great because on the board we already have the principal elements of life.
Organic chemistry is the chemistry of carbon.
Carbon fuses next, and still heavier elements begin to form.
Sulfur, argon, chlorine,
potassium, calcium, scandium. The pace of this gets faster and faster.
Back in the middle.
So you can understand here, this is where fusion is where all of our elements come from, and they come from stars in our galaxy fusing these things together. So I also wanted to go over an application of fusion. So I had said that fusion only occurs on stars, and currently that is not true anymore. Because of this year, there have been several places in the world that have actually sustained fusion or achieved major milestones in fusion. They haven't actually sustained it for too long a period of time, but they've made major accomplishments, and it can be said that they've sustained the temperatures and the pressures needed to achieve fusion. So one of these places is in the UK, and it's called JET, the Joint European Torus, and this is what's called a tokamak, and it's a type of reactor here that lets you speed up particles and get them really, really hot. And so they're running experiments with deuterium and tritium. Remember I said that was a heavy hydrogen, so that's hydrogen 2 and hydrogen 3. So these are hydrogen isotopes in order to achieve fusion on Earth. And so this has been, the research for this is long-standing. It's been going on since the 1980s, frankly. And as of this year, they've achieved major milestones for it. And they've been able to achieve fusion for decent periods of time, a couple of seconds, which is a major milestone because they couldn't even get that earlier. So let's check it out, what this looks like. So I'm going to show you the reaction inside of the tokamak.
2, 1, 0. This is the record-breaking reaction. It is more than 150 million degrees centigrade.
It's super hot. It's called a burning plasma.
10 times hotter than the heart of the sun. And it happened here, the world's most powerful fusion plant, Jet Fusion, in Culham in Oxfordshire. It is, say the team here, a landmark for this technology.
These results are really significant because what we've managed to demonstrate inside Jet is that we can create a mini sun, the right kind of mini sun, hold it there for a sustained period and get really good performance levels, which is a major step forward in terms of our quest to get to fusion power plants.
Most nuclear reactors use fission. That's when big, unstable atoms like uranium are split in two, releasing lots of energy and radiation. Fusion is different. It involves forcing atoms of hydrogen together, fusing them to create helium, as well as lots of energy and just a tiny bit of short-lived radiation. Creating mini-stars inside reactors like this is one of the greatest technological challenges humanity has ever faced. Get it right, and it holds out the potential for producing almost unlimited supplies of energy pretty much forever. The key.
So that's really incredible that we've been able to advance that much in science and see this in our lifetimes. So there's another place in the United States called the National Ignition Facility that's also achieved fusion as of this year, using a different method than a tokamak. So they actually fire a bunch of lasers at a source, a little capsule, and when the capsule collapses, that's when the fusion is achieved, and they hold this in a very specific type of reactor. It's called a hohlraum. It's essentially a tiny little metal thing, and all the lasers are all centered in here. And they hold it at a super, super cold temperature in order for this to happen. That's why it has to be cryo-cooled and helium. It's a very fancy device. And this capsule is where all the magic happens and where fusion occurs. So as of this year, the United States government lab, where the NIF is, the Lawrence Livermore National Lab, they actually produced a few 9-volt batteries worth of energy. So it doesn't sound very significant, but what they're doing here is they're achieving fusion and they're actually getting energy from it. So before this, they weren't even able to get energy from it. They were just doing fusion and they weren't getting it quite started. But they've been able to get fusion started now. So you can kind of see the comparison here of what's going on with this quote. It says, these NIF shots channel the energetic equivalent of a 0.5 kilogram of exploding TNT. So that's how much energy has to be put into these things, into this itsy bitsy tiny little capsule. And they only get about 10 times less energy out. So the goal is to get the equivalent out of it and get more out of it, right? Like you want to initiate it and then make enough energy that it's worth all that input. So we haven't gotten to that point yet. And that's what's called ignition, when what you get out exceeds what you put in. So this is the hohlraum here. It's itsy bitsy tiny. And this is where they're firing the lasers at the heavy hydrogen, the deuterium and tritium fuel inside the capsule. But they have achieved that burning plasma condition, that super duper hot temperature, and got it to output some heat. So that's really a big milestone. And now that they've achieved this, people are getting really excited because it looks like fusion energy is more achievable. And we might hopefully be able to see fusion reactors in our lifetime. Okay, so now I'm going to ask you, after learning all of this, see if you can distinguish the differences between nuclear fission and nuclear fusion. So there should be about 2 or 3 things that you can list for each. So some of the major differences between fission and fusion. Fission, one of those is it happens with heavy elements. Nuclear fusion, this happens with lightweight elements, so usually like hydrogen, sometimes helium. Fission happens at mostly room temperature, whereas your fusion has to be the heat of the sun, so very, very hot. Another thing about fission that's different is that it generates nuclear waste. So this takes a long time for it to become unradioactive, so that stuff does have to be stored. Nuclear fusion, on the other hand, generates stable products or very, very short-lived radioactive products. So there's a lot less waste that comes from the process of fusion. So now see if you can list the similarities between nuclear fission and nuclear fusion. How are these processes similar? See if you can list like 2 to 3 things. So chemically, we want to think about what's going on here. One of those things is that new atoms are being created in each sense. So we're going from one thing on the periodic table to another thing on the periodic table, which I equate to kind of like magic. It's kind of like alchemy, right? And then we also have a chemical reaction inside of the nucleus of the atom. Whereas normally when we talk about chemical reactions, we talk about electrons, right? We're always talking about electrons. We're talking about these things out here. This is where the electrons are. Whereas when we talk about nuclear reactions, we're talking about the nucleus. We're talking about the neutrons and the protons. It has nothing to do with electrons very much. And the other thing that's similar about these is they generate tons of energy, which is why they're kind of the holy grail of energy production. So you get a lot of bang for your buck. And that's all that we have to learn on nuclear chemistry for this topic.